Now let's go to MatrixMatrix Multiply. Right, so what do I want to do? I have two matrices. A, B, I want to compute A times B and store it in C. For simplicity right now I'm going to assume that they're all n cross n. How should I distribute this? Each row of the final matrix is given to a particular thread. Okay, let's see how that works. So I give this to thread 0. Okay, first let's talk about this approach, then we'll go to that one. What does thread 0 need to fill up these entries? The entire A and the first column of B, right? That's a matrix vector product. A times the first column of B will be the first column of C, right? So essentially what I'm doing is the matrix vector product, right? I take this entire matrix, I multiply it with this column and I generate the column of C. So what are the issues here? One issue is C is not being accessed contiguously. That's okay. Why? Because I only need to update C at the end. I don't need to keep on updating it, right? Is this point clear? So I multiply this whole row with this column, then I generate one element of C. So there are, the order of n multiply adds being done before I do one update of C. So C not being contiguous is an issue, but not such a big issue. But B not being contiguous is an issue, right? Because I have to access this B again and again and again, right? And it's not contiguous. So I'm not getting the benefit of data locality, right? Okay, that's one approach. That take the transpose of B and then do row multiplications, right? Yeah, that's one option. You have the transpose overheads. How do you write an efficient matrix transpose? That's another interesting problem. Okay, but we won't go there right now. What else? Here's another issue, right? So this is important. So typically we have to see that what is the compute to memory ratio of the operations we are doing. How many compute operations am I doing and how many memory operations am I doing? So if I'm doing more memory operations, so typically what happens in processors is that you have much more computational capability than you have memory bandwidth, right? So you may only be able to fetch one data element every 5 nanoseconds or something, but you can do computations in every nanosecond, something of that sort, right? So you want to have more compute, you want to be doing more computations than memory accesses. Let's just go back to the other operations that we did first and then we'll come back to matrix multiply. So what is the first one we did? We did a dot product. What is the number of compute operations I do in dot product? 2n? N multiplications, n additions, right? What is the number of memory accesses I have to do? 2n, right? Is that clear? But I have to do 2n memory accesses. I'm only working on each element only once, right? So I can't get around this. This compute to memory ratio is 1. The number of compute operations to the number of memory operations is 1. Okay. Yeah, what about this? What is the total number of compute operations I'm doing? Matrix vector product, number of compute operations? Don't give me the exact, just give me the highest order term and the constant associated with it. 2n square. And what is the number of memory operations I'm doing? I would argue it's 2n square. Maybe you can reduce it to n square. Well, you definitely have to pick up the entire A matrix. And it depends on how you work on X. Okay, if you are first multiplying the first row with the entire x column, then by the time you do that, your data is going to go out of the cache, right? So for the next row, when you start multiplying that with x, x is not in the cache. If these matrices are large, if these matrices and vectors are large, if n is large. Is this point clear? If you're working with large matrices, as you generally have to do in scientific computing applications, by the time you finish one row, if it has like, let's say 10,000 elements, you're loading 10,000 elements, that's about what? 10k elements, each is 8 bytes, so this is about 80k. That's huge, right? L1 caches are smaller than this, 32k, 64k. So you're going to end up doing about 2 n square operations. Let's forget that also. You have to at least pick up this entire A, right? You have to do n square memory loads. So you're going to get about 2 maybe in the best case, even if you're able to reuse your x properly. 2 is not good enough. 2 compute operations for every memory load, not good enough, right? You're still memory bound. So dot product was also memory bound, matrix vector product is also memory bound, and there's nothing you can do about it. These operations are known to be memory bound. What about matrix multiply? Forget about the algorithm. How much data is involved, first of all? What is the minimum number of loads you have to do? Load stores. 3n square is the number of memory operations that I have to perform, right? And what is the amount of computation I have to do? It's order n cube, right? Roughly about 2n cube. If I am able to reuse data, I may be able to do something better. So I want to be compute bound. I don't want to be memory bound. I want to come up with an algorithm that is compute bound. I may not be able to design an algorithm where the compute to memory operation is of the order of n because of the limitations of the cache size, right? But I want to reuse the cache size as much as possible and come up with a good enough bound so that I am compute bound. So what is the problem with this algorithm that we just discussed? So what is the last thing we were discussing? You take the entire matrix A, you multiply it with the column of B, and you get a column of C, right? That's what we were discussing. If one thread is doing this, how many load store operations is it performing and how many memory operations is it performing? It's essentially a matrix vector product. So that ratio is going to be 2. I want a much higher ratio to be compute bound. So that's where this scheme lacks. So any ideas? What can we do then? How do we generally write the code for matrix multiply? For I is equal to 0, I is less than n, I plus plus. For j equal to 0, j is less than n, j plus plus. Right? And then c ij plus equal to I'm assuming I've initialized C outside, right? Now if I simply add a hash pragma OMP parallel here, how is it going to distribute? So it's going to give one row of A at a time. Right? This is the first for loop. That's what it's going to divide, right? This is the only loop that gets divided amongst the threads. So once a thread gets a particular iteration of I, it is going to execute this entire piece of code for that value of I, right? This point is clear, right? The only thing getting divided is the first for loop amongst the threads. And so it's going to work over the entire B matrix, multiply it with this vector of A and store it where? In the corresponding row of C. And this is also a vector matrix product, right? This is same as matrix vector product. It's a vector matrix. So this is also memory bound. Same issue. If I swap these two loops and then I put hash pragma OMP parallel for, so the first loop is, let's say, j and the second loop is I, then what would it be? it would be a column of B and the entire A, and you would end up producing the corresponding column of C, right? And we've just discussed that I want something better. Okay, before we go to something better, so there's something called the collapse clause. What this does is, so if I say collapse 2, it basically clubs these two loops together, the two immediately occurring loops, and then divides them up amongst the threads. Okay, so in this case, each thread will get an ij pair to work on. So what is the distribution of work? How is the work divided? What is each thread getting? Each thread is getting one row of A, one column of B. So it will get one row of A, one column of B, and it will update that particular Cij. It's updating one element of C. But what is the best way of doing it? We just discussed, right? I want to reuse the cache because I know that there is scope, because the number of compute operations is much more than the number of memory operations, but I'm still constrained by the cache. So what can I do? Here's one way of doing it. So let me not directly jump to blocks. Let me divide this up into blocks of rows, and let me divide B up into blocks of columns. Now I give this to thread 0. So thread 0 takes care of multiplying this entire submatrix with this submatrix, and what does it produce? It produces this particular block, right? So what is the problem here? So the only problem is again cache reuse, right? So by the time I traverse this entire row and multiply with this entire row, and I traverse this and I traverse all these elements and multiply them, this first data element would have been thrown out of the cache because these vectors are so long. So here's what I do. I just divide them into blocks. Let's say of size B cross B. How do I choose B? So I have to look at the cache size. I have to be aware of the cache size to know that what is the B I should choose. But what happens now? Let's say that I give this block of C to thread 0, right? So what does it need to compute this? Well, what it needs is, it needs this block of A, this block of B. It will multiply them together, right? So let's call these blocks something. Let's give them a name. So this is A11, A12, A13, A21, A22, A23. So these are blocks. Each is of size B cross B, right? And this is C11. Yeah, ideally I should start with 0, but yeah, it's fine for now. So how do I compute C11? C11 is A11 times B11 product of these two submatrices plus A12 times B21 plus A13 times B31. Right? If I multiply these submatrices, these pairs of submatrices, then I get my block C11. Okay, you have to convince yourself of that. It's easy to check. You can verify. All right. What have I gained by doing this? So let's say I do this operation on A11 and B11. I do this product before I touch A12 and B21. I don't go row wise. I load this entire block, I multiply them, then I go to A12, B21, right? So I go block by block. So now in doing A11 times B11, if that entire data fits into the cache, what is the number of memory operations I have to perform, and what is the number of compute operations? What is the number of compute operations? 2b cube, right? And what is the number of memory ops? 2b square or 3b square? that depends on whether my C also fits into the cache or not. Right? I have to load these submatrices of A and B. Now can I write back the submatrix of C or not? If it fits into the cache, then I only incur an overhead of 2b square. I mean, I incur a cost of 2b square. The number of memory operations is 2b square. Right? So you see the difference now? So now you are able to achieve something better, right? You are able to get much better compute to memory ratio. So now what does it depend on?
Really, we were getting order of n.
We were not getting order of n. That was theoretical, right? We didn't have an algorithm to do that. I want to achieve this. That's what I was saying. You can't achieve n because you're limited by the cache size. So here we were making the point that maybe there exists an algorithm which can achieve this. There is scope. That's all I was saying. In case of vector-vector operations, there is no scope because the number of operations you have to do, you have to fetch as many elements as the number of operations you have to do. In case of matrix vector, there is no scope because the amount of data you have to load is proportional to the number of operations you have to do. So there is no scope. And then we said that in matrix multiply, there seems to be scope. The number of compute operations I have to do is much more than the number of memory ops. I want to achieve that now. So how do I achieve that? What is the algorithm to achieve that? I want to achieve n, but I cannot achieve n. If I have infinite cache, I can achieve n. Right? I can load the entire matrices into the cache and then I'll be done. But I can't achieve n because I don't have infinite cache. So I'm bound by the cache size. So therefore I said that if B is a number such that 3 submatrices of size B cross B can together fit into the cache. A submatrix, B submatrix and C submatrix. If all 3 of them can fit in the cache, if there exists such a B, then I'm going to achieve this ratio. Right? So what is the practical value of B? So if I choose, let's say B equal to 32, right, then how much data do I want to load into the cache? 32 into 32 is the size of the submatrix A, and each element is 8 bytes, so this is about 8k, right? And then there are 3 such matrices, so 24k. Not bad. Doable, right? You have L1 caches which are typically larger than 24k. 32k, 64k, these are reasonable sizes. If you have 64k, you could try to get even better.
But in this approach, we have to use locks.
Why do you have to use locks?
Because when I'm giving A11 and B11 to one thread, A12 and A12 and B21.
Right.
It's given to another thread and there is
No, what I gave to thread 0 was C11. That's what I distributed amongst the threads, the blocks of C. Once thread 0 is responsible for C11, it will do all these computations, but it has to rearrange the code. It can't be in the form that we wrote it a little while back, right? This is not the code to achieve that. It has to work this way. It has to first do A11, B11, then A12, B21, then A13, B31. Right? It's just the order in which you write the code. So a lot of these things are valid even for single processors. When you're writing multi-core code, you have to know how to distribute the work amongst the threads, right? And for that you need to know which are the most optimal algorithms. So what kind of speed up have I achieved? Roughly about B, right? And if B is 32, then I have been able to achieve a compute to memory ratio of 32, which is not bad. Right? On most processors it would be reasonable. I should be able to cover for the memory latency with the compute time. So typically, how do you write these codes? I mean, we are not going to go that far, but how do you optimize this even further? So what you do is that while the processor is computing A11, B11, it will keep issuing instructions to fetch A12 and B21 into the cache. Right? But then you have to hold not 3 submatrices, but 5 submatrices in the cache. A11, B11, the next A12, B21, and C11, right? 5 submatrices. So then you have to choose your B accordingly. But then you can completely, hide the memory latency behind the computations. So I can interleave instructions in the code to fetch that data into the cache. So there are instructions available to prefetch data into the cache. As I said, we are not going to go down to that level, but you can do all those.